In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller was ready to answer the call. With his flute in hand, Miller played a tune that echoed through the cosmos. Each note, a shot of pure ether, struck the Einsteinian demons, dispelling them back into the void. The world was saved, not by a warrior, but by a musician, a scientist, a man with a flute.
All right, boys, we're live.
Hello, everybody. Welcome to Ether Cosmology Reading Night. Tonight, we're going to get right back into the old Seeing Red by Halton ARP. We are on chapter 4, although we did read a couple of chapters from later in the book previously. So when we get back to those, I assume we'll probably, if or when we get back to those, we'll probably just read them again because
Yeah, for continuity.
and a bit continuity. Yep. Although even these have been spread across multiple different reading nights. So if you want to go find it all, you'll have to maybe do a little spelunking. But in any case, we are on chapter 4 of Seeing Red by Halton ARP. If you need to get a hold of the document, reach out to one of us, or you can, of course, pick up a hard copy for yourself. And so the standard disclaimer here on Monday nights is that this is reading and research live on the spot. It's not a presentation. It's not us trying to, sound pretty. Literally just live reading, live research. Sometimes us fumbling through different words and equations and such as we learn. So that's the disclaimer. If you're looking for more of a standard presentation, check us out. On Tuesday nights, we tend to do presentations. And then on Thursday nights, we do live discussions on X Twitter Spaces. And check out what Shane and Alan have been up to. And and of course, check out what Stone's been up to as well. So without further ado, let's do some reading. And I'll go ahead and get us started here tonight. And if anyone wants to pick up at any point, just let me know. But let's get going. So if we are to believe the previous 3 chapters, then most
All right, so Toby took a quick nap. Oh, okay, he's back.
That was odd. I don't know. Discord just randomly shut down on me.
Just decided you were done reading
Good start.
it.
I guess it didn't like your language.
Yeah, I was right. I think my stream is still good. Let me double check here. I think so. Yeah. Cool.
Yeah, you're up.
Excellent. Thank you, Stone. All right. So let's just start from the beginning again. If we are to believe the previous 3 chapters, then most extragalactic objects have intrinsic redshifts, ranging from large values for high redshift quasars and continuing right down to small values for low redshift galaxies. It was important to discover that low and medium redshift galaxies also had non-velocity redshifts because it meant that the effect pertained not only to quasars, which could be argued to be exotic and not well understood. Now, the phenomena could also be studied in nearby galaxies having gas, dust, and stars, which could be resolved individually. All components about which we thought we knew most of what was important. The Magellanic Clouds. The 2 nearest galaxies to us were reported as faintly luminous clouds in the southern hemisphere by early explorers. Even with the 74-inch telescope in South Africa in 1955, I was able to measure 10 magnitudes fainter than the brightest stars in the South Magellanic Cloud. But it was not until 1980 that the brightest supergiant stars in both clouds were measured with high spectroscopic dispersion. Now the Magellanic Clouds are members of the local group of galaxies and therefore have an intrinsic redshift relative to the oldest galaxy in the group, M31. They also have positive redshifts with respect to our own Milky Way galaxy, which would mark them in turn as our younger offspring. Huh. One could not help wondering about one could not help wondering whether the gas, dust, and stars in these smaller neighbors had all shared the same excess redshift, particularly the supergiants, which are short-lived and must be in some sense younger than the rest of the galaxy. I remember vividly when long ago I first checked the companion galaxies to see if they were redshifted with respect to the dominant galaxy. It was with the same sense of not daring to hope that I now approached the necessity of checking the supergiants in the Magellanic Clouds to see if they were, by any chance, redshifted with respect to their own galaxy. So redshifts of supergiant stars in the small Magellanic Cloud and the large Magellanic Cloud, corrected for stellar wind outflows, whatever that means, that's highlightable. Let's do green. Corrected for stellar wind outflows, it is seen that most luminous stars in our nearest neighbor galaxies are systematically shifted with respect to the mean. Wow. Okay. Yeah. Okay. They were. Huh. The accurate redshifts tabulated by John Hutchings in his study of their low mass properties revealed at a glance that there was a systematic redshift. One had to one just had to run one's eye down the column of redshifts. Of course, the mean redshift of the gas in the Magellanic Clouds was known to within 2 kilometers per second. The mean redshift of the older stars, though less accurate, agreed very well with the gas. Only the bright supergiants were systematically redshifted, and it would be absurd to suppose that just these stars were running away from their galaxy in the direction we happened to be looking. When I showed this result to some knowledgeable colleagues, they immediately responded that you could not trust redshifts of stars with with mass loss winds. They were sure that what I was seeing was an effect of the velocity of those winds and the measured redshift. Stellar winds, bright supergiant stars pour out so much radiation that the pressure causes mass loss, winds to leave the surface. As we look at the star, the intervening cooler gas, which causes the absorption lines in the spectrum, is moving towards us and therefore has a negative spectral shift. I did not know much about stellar winds, so I had to draw a simple picture many times over to convince myself that the redshifts measured from absorption lines coming toward us would have to be made even more positive by correcting for this negative velocity component. Since the spectral characteristics had been correlated with the speed of the stellar wind in these supergiant stars in the SMC and LMC, it became possible to correct numerically for the outflow velocity. When this correction was made, all 10 supergiants in the SMC and 20 out of 24 in the LMC were positively redshifted with respect to their home galaxies. This is shown in figure 4.1, which we looked at earlier. This is a devastating result because one need only look at the distribution of redshifts to realize that this could not be a chance occurrence. My colleagues still insisted that I must be applying the wind correction in the wrong sense. So I consulted the world expert in stellar mass loss, Rolf Kadritsky, who conveniently happened to direct the Munich Observatory. He was very helpful, invited me over to give a colloquium to his group, and verified that the corrections were being correctly applied. In fact, he dug into his group's observations to supply me redshifts on additional supergiants that were made at the base of the photosphere where the wind was just beginning to accelerate to its final velocity. These turned out to be independent checks of the positive stellar shifts. At this point, I recalled sitting in Bart Bach's astronomy course at Harvard and listening to him describe the mysterious K effect. This is the effect that W. W. Campbell discovered in 1911, namely that the bright blue stars in our own Milky Way galaxy had systematically higher redshifts than the rest of the stars, With my undergraduate self-confidence, I set out to write him an equation that demonstrated how the young stars were streaming out from our galaxy. With some difficulty and a great deal of patience, he finally convinced me that they should not be streaming away from just our sun's position on the edge of the galaxy. So gradually, the problem receded from the front of my mind. But empirically, this is the same effect that I had just found 40 years later in the Magellanic Clouds. Wow. Actually, what had triggered my memory was a paper by a Canadian physicist, Paul Marmé. Huh, our boy.
Shout out to the Hobie.
He was arguing the case that photons traveling through interstellar and intergalactic space would lose some of their energy by inelastic collisions. He had made a quite summary of the old evidence for the K effect in arguing for the tired light origin for redshifting of galaxies and stars. So, what is tired light? Over the years, many people have argued that photons lose energy on their long voyage through space. Yeah, it's a long ways to go, homie. Uh, Pack your bags, little photon. This is an extremely reasonable idea since the distances are the largest we have experience with. Yep. Distances are largest we have experience with. Yeah, let's just highlight that right there. Boom. But there are several observational arguments that persuade me that this is not an important part of cosmic redshifts. The first is that we look to lower galactic latitudes in our own galaxy. We see objects through an increasing density of gas and dust until they are almost totally obscured. No increase of redshift has ever been demonstrated for objects seen through this increased amount of material. Secondly, we have seen that if we look through extragalactic space, the example of quasars linked to low redshift galaxies demonstrates that two objects at the same distance with closely the same path length can have vastly different redshifts. Finally, if we say there are clouds of a redshifting medium around each individual object, then there should be gradients of redshift across resolved objects, which are not observed. Further, we should see silhouetting and discontinuity effects between adjacent objects, which also are not observed. Perhaps on some level, light can get tired, but does not appear to be significant in the redshifts we are dealing with. The K effect. When I realized that the excess redshifts of young stars in the Magellanic Clouds furnished a confirmation of the K effect in the Milky Way, it reminded me that no satisfactory explanation had ever been advanced for the phenomenon. When I went back over the literature, it was clear that the lack of explanation had gradually led to a disregard of observations having nothing to do with the problem. Plaskett and Pierce in 1930 and 1934 had tried to explain it as streaming motion, but it had to be over a huge sector of more than 120 degrees in the sky. Smart and Green in 1936 concluded K must be regarded as a systematic correction to the radial velocity of B-type stars. Robert Trumpler, a well-known galactic astronomer at Lick Observatory, took a different approach, referring to the redshifts as of OB stars, not to a large volume of other stars, but to redshifts of the younger clusters to which they individually belonged. In 1935, he reported an excess redshift of 10 kilometers per second from a sample of 9 of the most luminous stars in 6 clusters. Now, Trumpler believed he had an exciting confirmation of the much publicized theory of general relativity. But when the strength of gravity at the surface of these stars was calculated, it was found to be much too weak to give a gravitational redshift as large as observed. The rest of the astronomical community promptly forgot the K effect, but Trumpler went on believing it to be a gravitational effect and continued to quietly measure more stars. In 1955, he presented his accumulated results in a conference in Bern on the 50th anniversary of relativity theory. There were 18 stars in 10 clusters, which gave a mean excess redshift of plus 10 kilometers per second, plus or minus 1 kilometer per second. This result had a chance of about 1 in 300 billion of being accidental. But we should also note that Trumpler measured his own O stars relative to the early B stars in the cluster. As Finley Freundlich pointed out, the B stars themselves have a K effect, which approximately doubles the net excess of the O stars reported by Trumpler. Many other investigators had found the same effect in other associations of young luminous stars. For example, the renowned stellar observer Otto Struve had shown that these types of stars in the Orion Nebula had excess redshifts of plus 15 kilometers per second. When corrected for stellar winds, these numbers were close to the average values found for the SMC of plus 34 kilometers per second and plus 29 for the LMC. So it's talking about those 18 stars in the 10 clusters, which gave a mean excess redshift of plus 10 kilometers per second. Most astronomers have never heard of that result. The only reason I know about it is that Jürgen Ehlers was at the meeting and gave me the reference. It is interesting to ponder the implications. Let me give that a little green.
Dude, he's got that insider info.
I love this. It is interesting to ponder the implications. It is interesting. Sounds
What
interesting.
did I do with my lighter there, Jack? Oh,
A little hot mic there. All right. So redshifts at the most luminous members of the H plus Chi or Chi Persei star clusters in our own galaxy. Open circles are luminosity class LA, half-filled circles class LAB, filled circle LB, and circled cross class MLAB. Again, the youngest stars are systematically redshifted. Wind corrections should accentuate the effect. So H plus Chi Persei. Or Chi? Chi? We'll go with Chi.
Yeah, Chi sounds nice.
Anyone want a popcorn?
Yep, I got you. Give me 1 second. Let me get some water.
Yeah, I need to do the same. If not, I can pick back up, but I do just need to drink some water real quick here. I can keep going if you want, Alan. I don't
Yeah,
mind.
I need like 2 more paragraphs.
Cool. No problem. No rush. I also just wanted to, if anyone else wanted to read, but I can keep going. My pleasure. So H plus Chi Persei, considering more recent results, the most prominent aggregate of supergiant stars, which springs immediately to mind, is the double cluster that can be seen with the naked eye as 2 faint smudges in the constellation of Perseus, i.e. H plus Chi Persei, or Chi Persei. It is in the next spiral arm outward from our own and, and contains some of the brightest blue and red supergiants known in our galaxy. After I consulted the latest measures on these stars by Roberta Humphreys, it was obvious to me that the brightest among these young stars were on average the most redshifted. Figure 4.2 shows how the brightest have about plus 15 kilometers per second excess redshift from stars only a little more than 2 magnitudes fainter. These fainter stars themselves undoubtedly have some K effect. And of course, the mass loss correction which must be applied is even stronger for our galaxy because it has relatively high metallicity. Although the magnitude of the excess redshift for the brightest stars in this best known galactic cluster must be in excess of plus 30 kilometers per second, quite like that which pertains to the Magellanic Clouds. As a side comment, we should note that since these corrections have not been taken into account, the spiral arm kinematics derived for our own galaxy must, to some extent, be wrong and should be recalculated. It is interesting that when I sent these results to the researcher responsible for measuring the H plus Chi spectra and asked for comments, there was no response. K effect in other galaxies. The K effect can be tested in other nearby galaxies if there is spectroscopic evidence of young, high luminosity stars. What shows up in the composite spectrum is absorption lines of hydrogen, particularly the higher excitation lines, which are sharper in the rarefied atmospheres of young giant stars. As an example, a nearby dwarf galaxy called NGC 1569 is shown in Figure 4.3. On one of my last runs at Palomar, I took spectra of the two stellar appearing objects in the center of this peculiar dwarf. Gerard de Vaucouleurs had thought they were radiation from high energy electron gas, synchrotron sources, but to my amazement, they turned out to have sharp line spectra, exactly like a very bright supergiant. Figure 4.3, the deeper exposure shows the dwarfish morphology of this nearby active galaxy. The weaker exposure shows the two clusters of young stars which dominate the interior of the galaxy. These clusters are redshifted by 36 and 35 kilometers per second with respect to the mean of the galaxy. I mean, so you've got stars. Isn't that cool? Everything is expanding away from everything is expanding away from everything else infinitely faster than the speed of light from a non-existent central point. But and everything's doing this perfect little loop-de-loop, these perfect circles, concentric or concentric slightly elliptical circles, or elliptics if you want to call them, ellipses. But then you've got these supergiants in the middle of these galaxies, in the middle of all of this, that just for whatever reason just look like they're moving toward or away from us directly at totally random, like totally different rates than what everything else shows. Ah, cool.
Hey,
Let's just forget about all that and never talk about this guy that we named a galaxy after ever again.
how about when you email the guy in charge of measuring the chi spiral or whatever, he doesn't email you back. He's like, hey, you know that redshift spiral you think you have calculated? You should redo that. And the guy just never replied. He just had better stuff to do. Like he was probably calculating, some real hard differential equations or something. As they do.
Oh, and the Flintstones are on.
So on one of my last runs at Palomar, I took spectra of two stellar appearing objects in the center of this peculiar dwarf. Okay, so yeah, we just read this paragraph here. In Figure 4.4, the spectrum of the brightest one of these objects is shown to have such a low density atmosphere that the hydrogen lines are so narrow that they can be easily seen down to H12. In lower luminosity stars, one does not see the hydrogen series so narrow. Composite spectra of average galaxies principally show the H and K lines of calcium. Under higher resolution, these objects later turned out to be the compact star clusters, in which the stellar orbital velocities were not high enough to broaden the spectral lines. It is intriguing that these clusters are double as the H plus chi per se cluster in our own galaxy. There are many examples of double cosmic objects, but the question of why has not even been asked, much less an answer attempted. With such good spectral resolution, the narrow lines can be measured accurately and compared to the accurate radio measures of the neutral hydrogen in which most young galaxies are embedded. In the case of NGC 1569, as Table 4.1 shows, the bright stars in this young double cluster are just about plus 35 kilometers per second higher redshift than the hydrogen in the galaxy. This is the same situation as in the Magellanic Clouds, and of course, the mass loss corrections could make this excess redshift even larger. Finding obvious evidence for intrinsic redshifts in a number of independent analyses of objects which we think we know as much about as stars is a sensational development. Moreover, as we shall see later, the relation between young age, low mass to luminosity ratio, and increasing redshift is crucial to discovering the cause of the intrinsic redshift. So under high resolution, these objects turned out to be compact star clusters. And when he said that, he says, when we wrote a paper about this observation, Sandage voted for the star cluster interpretation, and I voted for single stars. Sandage turned out to be right. Okay. So figure 4.4, we show the spectrum of the brighter star cluster in NGC 1569, showing the narrow hydrogen absorption lines, which mark the stars as evolutionarily young. Take that for whatever it's worth to you. It is not a discovery until it is communicated. Gathering all the above material on stellar excess redshifts together has furnished quite an impressive demonstration of the effect. The excess redshifts of the Magellanic Cloud supergiants were especially striking since the mean redshifts of the galaxies were so accurately known. Consequently, I thought it appropriate to submit it to the French editor of Astronomy and Astrophysics because he was a specialist in the clouds and had just finished an extensive study of the hydrogen gas in them. How naive of me. The paper came back with not just a rude, but a savage rejection. To answer one objection, I undertook the enormous task of differencing the redshift of each supergiant with the local hydrogen in its immediate vicinity. Of course, the result was the same. The paper came back with an even stronger rejection and the suggestion that I should have presented it as proof of the incorrectness of the spectroscopic redshift measures. Wow. Okay. So table 4.1, intrinsic redshifts of stars in nearby galaxies. So OB stars in Milky Way, K effect plus mass loss, 0.6 to 22. So looks like we're looking at differences here in this column. Pretty drastic. So here's the Magellanic Clouds. Yeah. Very interesting. Looks like pretty well observed all over the place. The aspect that upset me the most was that this very important scientific data was being censored by an editor whose primary responsibility was to communicate such data. After some anguished thought, however, it occurred to me that establishing the principle that it was the foremost obligation of the editor to publish valid scientific data was even more important than communicating the data. As in other cases, I convinced myself that if people faced with clear cases of improper conduct did not take a stand, there would be no hope for the reform. And in fact, matters would probably get worse. So I set about the daunting business of finding out who the editor board or who the editorial board was, writing a summary, including the pertinent materials, and making an official protest. It turned out the then director of the institute where I had taken refuge as a guest scientist was at the meeting of the European Council, which considered the complaint. He never said anything about it to me, but one of my other colleagues heard about it and was furious at me. As far as I know, my protest did not accomplish anything. But I did find out that the editor in question was on the visiting committee of my host institution. I was pretty miserable about the whole affair, but I still felt I had done what I had to do. Wow. Well, I'm glad you wrote your book here so we can all learn what you did, man.
Stuck to his
All
guns.
that, of course, had...
I can take over if you want to take a break, Toby.
Sure.
Okay. All that, of course, had not solved the problem of communicating the data. With the trepidation, I then submitted the paper to the monthly notices of the Royal Astronomical Society. Great day. I got a referee while who, while a little grumpy, accepted the paper. I had felt it made an impressive case when finally published the MNRAS. Yeah. Anyway, but that I thought was that another important development dropped into the black hole theory. I was hang on, this cat is killing me. Relax, buddy. All right. You should be all right. I was astounded sometime later when I got a telephone call from the foremost expert on the luminous stars of the Milky Way, Aldrin Blah. Stone, is that how you'd say that? Blah.
It's just Adrian Blau.
Oh yeah, Adrian Blau. My bad. I was close. Adrian Blau. As an old astronomer, he harked back to an era when astronomers studied and really knew about the stars in our own galaxy and really knew about them. He said that the paper should have been written 10 years ago. I have felt euphoric. He came to my office later and we talked a length about it. He got some of the students to invite me to a colloquium, but most of them sat warily silent, and one or two tried to rework the observations to fit conventional assumptions. After that, it slid downhill in a way that was help me out.
Instructive.
Instructive, really? Okay. That is instructive to recount. Two, with the modern astronomers still working with the K effect, were measuring the luminous O and B stars. They had run out of the most luminous ones. Moreover, they did not correct for the wind effects, so naturally they found the smaller effects. They then made the most satisfying announcement. With the measurements of the sample of the large anomalous effects had gone away. About that time, Jeffrey Burbidge was starting to include the K-effect results in his lectures as further evidence for the intrinsic redshift. On one of the lectures, he gave a young astronomer stood up in the audience and said, "Oh, these positive wind effects have been observed in the sun, and they are easily explained." I talked to him after the lecture, and he did not have any understanding of either the sun or the supergiants. After another lecture at the IAU, one of the astronomers had come to the wrong conclusion from the test of the Trumpler effect with the fainter stars, and came up to Jeff and said, "Old friend, after making the most modern investigation, I have proved that the K effect doesn't exist. Now Jeff has been a real hero in forcing unwilling audiences to listen to evidence for non-velocity redshifts, but understandably that has stopped including the K effect in his presentation." Let's see, the Pleiades maneuver. Often when a proponent of a cherished viewpoint is threatened by a contrary evidence, he calls for further observations. This delays decisions, but is unassailably proper scientific position, but is an unassailably proper scientific position. It is apt to work out, however, in the following way. Let us say someone believes in a completely homogeneous universe. The Pleiades star cluster is an embarrassing observation. He says there are too small a numbers of stars to be statistically significant, so let us test this hypothesis by getting a larger sample. He measures the stars down to the 21st magnitude, the non-cluster background, and reports triumphantly that the clustering has decreased to the point of insignificance.
Wow.
Nice, dude. He just made it disappear with math, dude. That's what's up. You didn't know you could do that, boys? So that leaves the
I call that statistical annihilation. Sorry.
You're good. 1 second here. Gotta reset these crabs. All right. Let's see. That leaves the average non-specialist looking up at the sky, wondering how the clump of bright stars could be accidentally so conspicuous. NGC 2777, otherwise known as NGC numbers, henceforth. Deserving the special mention that this system, which contains the main galaxy NGC numbers and the companion galaxy NGC numbers, the companion has a very accurate measurement from these early type stellar spectrum. The system is sketched in figure 4-5, and the spectrum of NGC numbers is shown in figure 4-5. Or 4-6, sorry. In the spectrum of the metallicating.
Metal indicating.
Metal indicating. God, that hyphen threw me for a loop. Okay, so the metal indicating K line and the practical basant marking the galaxy as so young, the successive generations of the stellar evolution have not had time to enrich that metal content. Again, we find the younger stars with an accurately measured excess redshift, the K effect, of plus 31 kilometers a second, shown in Table 4-1. Again, this does not have a mass loss correction added, although the metal poor star's astropheric opacity is less than the stellar wind, and it does not blow so hard. Oh, it just has less wind, stellarly speaking. Let's see. This system is a particularly powerful example of a companion with a higher redshift than its parent, 193 plus kilometers a second, with respect to NGC numbers, the large neighboring SA galaxy. The companion even has its umbilical cord, a streamer of neutral hydrogen leading back to the larger galaxies. It is a quintessential example of a slightly younger, slightly higher redshifted companion galaxy just now emerging from its parent galaxy, as described in the preceding chapter, but now we see a younger generation of stars within it having higher redshifts still. The urge to merge. As mentioned in the previous chapter, some astronomers saw peculiar galaxies neighboring each other and immediately assumed that the peculiarity was caused by the galaxies falling into each other. By ignoring the empirical evidence for ejection from galaxies, they illustrated an unfortunate tendency of science, namely, when it is presented with two possibilities, scientists tend to choose the wrong one. Oh, no way. We can explore the... Can we get a statistical rundown of that? What the odds are? Let's see. We can explore the theory behind this observation later. Yeah, but let us examine the reasons why collisions of the unsatisfactory model for systems like NGC numbers and NGC numbers. 1. The hydrogen from NGC numbers leads to directly back to towards the center of NGC numbers, implying the companion originated directly from the nucleus. Two galaxies falling together would have the same transverse component of velocity, therefore not directly together, but have a parabolic counter. 2. Companions around the main galaxy would have an orbit around 15 billion years and would only occasionally fall in for an encounter. Nice. Just a 15 billion year timeline, plus or minus, you know. They would have to be like that huge Oort cloud of comets which supply the occasional visitors to the interplanetary system. Large reservoirs of companions are not observed around central galaxies. Unfortunate. 3. There is now simply an enormous amount of evidence that the companions are systematically redshifted. The merger/collision hypothesis would require as many companions approaching as receding. Why not publish it? The paper titled "The Properties of NGC Numbers Are Companion Galaxies Too Young" took 2 years, 3 months to be published in the Astrophysical Journal. The referee started out with comments like crackpot theories, twisted judgment, quite nonsensical, revolutionary conjectures, unsupported conjectures. After 5 revisions, formal complaints to the editorial board, and a detoured editorial intervention, dude had to get a mediator involved to deal with the complaints like too hard to be real or poorly organized. It was finally published. My favorite complaint was that NGC numbers had not been identified as the companion. Apparently, this referee had not read the title or the abstract or even looked at the figure. Dude, shout out to your boy referee. One referee contributed to an engaging smile. However, when he objected, it was ridiculous to imagine the new galaxies being ejected like popcorn from old galaxies.
Let's hear it for the boys at the Astrophysical Journal.
Holding it down for the lads, dude. Let's see here. The problem of the star formation. The problem of star formation. The field of research, the field of research, which
Hey, Alan, if he's only going to refer to the two of them, just call them 77 and 7 galaxy clusters, and he's only talking about two of them the whole time.
Oh, just 77 and 76? Gotcha.
75, yeah.
Oh, 75. Yeah, gotcha. Okay. The field of research, which the 77 observations had so deeply offended, was the merger scenario. But with more to it than that, because the 77 was clearly a starburst galaxy, which rapid current star formation was taking place. One of the major cornerstones of the conventional theory is that the stars are formed as the result of the collision of gas/dust regions. Excuse me. The idea is roughly that the gas would be compressed by by the shock of the globules and would collapse from and form stars. So, compressed by the shock and the globules would collapse to form stars. The old collapsing globules.
In a vacuum.
As far as I can tell, this right here is exactly how Michael Brenner eventually became a flat earther.
Yeah.
No doubt.
He got to that point, started going down that rabbit hole, and then he was like, oh no, none of this makes any sense.
Shout out to Michael Brenner, dude. All right, now my co-author, Jack Sleuthdick, and I were disrespectful enough to suggest the smashing of the lumps of gas together was the worst possible way to make a star. How dare you? That's going against all of it.
Dare you? That's
just slapping Newton right in the face. All right, it was just heated up gas and generally caused condensation to dissipate. We instead suggested that the key in star formation was the concentrate of gas as it cooled in the spiral arms of a galaxy, which the concentrates ionized in the magnetic tubes which defined the arms. Dang! Check out your boy utilizing the natural assumed mechanics of all that and how it would work if you were inside of it.
What the magnetic tubes? What the hell are you talking about?
Right.
Dude, don't they assume though that earlier they were talking about how there was like the rotation of all that produces a magnetic field and all that. So like it's in their religion. I'm just saying it was nicer than, space-time combustion theory.
disapproval expressed is all I'm saying.
Start again.
All right. Any directed ejections from the active nucleus would stretch out the magnetic field lines from the interior into the flux tubes, allegedly. The rotation of the galaxy would turn these into the spiral arms, and we were back to my old favorite, spiral arms as ejections, which then become loci for the new star formation. With anamorphously shaped starbust galaxies, perhaps the rotational disk of the material had not yet been formed. In attempting to publish the evidence for the ejection origin for the starbust companion of 77, we had to trod on a number of sacred assumptions, including merger included star formations, and the galaxies being old and only having a velocity redshift, or a velocity related to redshift, or a redshift related to velocity. Sorry. It was flattering that the majority of the field tried everything to block our discussion of these problems, but it was also terribly discouraging that when it was finally published in the Astrophysical Journal, absolutely no discussion ensued. Dude, they straight ghosted your boy. Nobody was super pumped to hear this new theory of magnetic tubes.
Or ARP.
All right. Let's see. starburst galaxies. Now that we have mentioned these galaxies, which everyone agrees contain a lot of young stars, we should make an attempt to relate them empirically to other galaxies and the characteristic groups in which they like other galaxies, occur. This is done in Table 2.4, where the best known starburst galaxies are listed. This way of doing business is not liked by academics. It is too simple, just like the prominent examples, and they see if they give a clear trend. One may not recall every case, but if the trend is clear in a few cases, it will not change it. If one goes to a less prominent examples, they will probably also confirm the relation, and if they do not, one must check that they are the same kind of objects. This method just requires a good acquaintance with the sky, or with what the sky contains, and can be done initially in the head. Nice. There is a clear trend in Table 4-2 of the brightest, best-known galaxies, which are classified as starburst, amorphous morphology, usually high surface brightness, young stellar spectral objects, and hot point infrared colors, which everyone agrees is a criterion of current star formation. The last two columns of the table then clearly show the starburst galaxies are companions to some of the largest, best-known central galaxies in the sky, and they are always the most redshifted with respect to that galaxy. Crackpot theory. Or whatever.
If that candy company wants us to say this correctly, they can monetarily, we can reach out. We can discuss.
The interim summary. The most important result so far is the empirical evidence as discussed in this book establishes a pattern whereby the large old galaxy has rejected the younger star material, or ejected the younger star material, and which has formed from the smaller companion galaxies around it. The younger galaxies in turn eject material which forms even younger quasars, the BL-LAC objects. The age hierarchy is evident from the properties of the objects and the characteristic groups in which the galaxies occur. The ejection origin of the younger objects is evident from the pairing across the active nuclei, their luminous connections back to the active centers of the general propensity for the injection, general propensity for the injection of the radio X-ray emitting material and excited gas. The one-to-one correspondence to the age hierarchy. There is a redshift hierarchy. Every testable line of evidence shows the younger the object within the groups, the higher the intrinsic redshift. But now we have to deal with the more rigorously with what young means for stars and galaxies. Age is just a number when it comes to galaxies or whatever they say, right? I think that's what I heard an astronomer say once.
4 billion is the new 10 billion, right?
I think so. The math checks out. Ages of the stars. Oh, here we go. Yeah, we're going to get into the legal logistics of it. Conventional star formation takes place in a gaseous medium in a vacuum, though, with a density fluctuation, gravitationally attraction to the ignition point of the nuclear fusion radiation. The gas could have been in existence for a long time, but the life of the star is viewed from the starting point of the origin or from the time of ignition. If the star then evolves for, say, a few billion years to, say, a fainter luminosity, then it is usually thought of as an old star. We will retain the term age as an indicator of its evolutionary stage, but we will introduce the concept of age of the material out of which the star or the galaxy is made. In the Big Bang Theory, all the matter was made at the same time 15 billion years ago. Thus, there is no concept of young or old matter in the current parlance. Let's see. But But here we will speak of a quasar being made out of young matter, more recently created matter, in order to account for this intrinsic redshift. Dang, check out your boy doing his own cosmological brainstorming. How would this work?
Respect it.
How would this work in the case of a real galaxy, say M31, and our own galaxy or Milky Way and the malogenic clouds? Figure 4.7 shows the parent galaxies created 17 billion years ago. Unlike the current Big Bang theory, which assumes that all matter was created instantaneously, we suggest it is vastly more realistic to create any given proto-galaxy over a small interval of time, about 6 million years, as indicated by the Gaussian distribution shown in figure 4-7.
Oh boy.
What's up? You bracing yourself for a nice distribution?
He's just getting into his, just an interesting leap to make. Oh, we're going to go down to 6 million. Okay.
Well, I think
Why?
he's trying to differentiate between how old the matter is versus how old the form is. That may have formed later out of the same old matter, but now you have a different formation going on, physically speaking, so that formation has a younger age than the rest of the matter.
Yeah, that is I get what you're saying. He is differentiating. Like, it's just funny that that's what he came to me. That's all.
The interval of creation would be 0.03% the age of the parent. Now suppose about 8 million years after the creation of the parent ejects new material which eventually evolves into a companion galaxy. As figure 4-7 indicates, the younger companion has a similar spread in the age of its material. Then the most recently formed stars in the companion will be preferentially composed of the most recently formed matter. This would account for the brightest stars in the melogenic clouds having small intrinsic redshift, with the brightest stars in our own Milky Way galaxy having the same order of intrinsic redshift. We will elaborate on this this somewhat difficult point in the later section, but we would first like to explain that the empirical result that the younger objects have a higher intrinsic redshift does have a theoretical explanation. The explanation, in fact, allows us to test the numerical relation between the age and the redshift.
At last.
Finally. We've all been waiting. How old are you, object in the sky that's irradiating energy? Why does younger matter have a higher redshift? In 1966, when it became clear that the quasars 3C273 was in the Virgo cluster and the other quasars were associated with the nearby galaxies, the intimidating question of what caused their redshift cast a foreboding shadow over everything. It quickly became clear that unless there was an acceptable explanation, the results would never be accepted, no matter how strong the observational evidence was. Nice. You don't include it until you can incorporate it and explain it as a prediction of Einstein. Got it. And if the result was not accepted, then the observation would lead to an explanation that could not be followed up. Rip. This is the insoluble dilemma which limits academia. Rest in peace. Can we get a little highlight on that? Like it just goes nowhere from them. Why don't you publish the paper? Like, yeah, do you think these dudes are going to be super stoked to go, oh yeah, there is a relationship between optical curvature and Earth curvature. we should check that out. All right. Oh yeah, that is weird. But the simple empirical pattern recognition in the observations did show that there was a continuous pattern or continuous physical transition between the compact, high redshift quasars through the surface brightness, active companion galaxies, and finally down to the more relaxed, normal appearing galaxies. This empirically was a continuous sequence in age from the youngest to the highest redshift to the oldest with the lowest redshift. But what was the cause? What was the reason that the youngest had the highest redshift? In 1964, Fred Hoyle and Janet Narlikar proposed the theory of gravitation. Nice, shout out to the boys. I would now like to prefer to call it the theory of mass, which has an origin of mass principle. According to the theory, every particle in the universe derives its inertia from the rest of the particles in the universe. Imagine just an electron born into the universe before it has time to, quote, see any of the other particles in its vicinity. It has zero mass because there is nothing to operationally measure it against. As time goes on, it receives signals from the volume of space and enlarges at the velocity of light and and contains larger and larger number of particles. Its mass grows in proportion to the number and its strength and the strength of its signal it receives. All right. Now comes a key point.
Sounds interesting.
Pretty cool. Now comes a key point. If the mass of an electron jumping from an excited atomic orbit to a lower level is smaller, then the energy of the photon of the light is emitted is smaller. If the photon is weaker, it is redshifted. We will explore rigorously in the cosmology chapter, but it suffices here to understand that the lower mass electrons will give higher redshifts, and the younger electrons would be expected to have lower mass. Of course, the mass of the particles scale together, but it's primarily a change in the electron mass which determines the change in the wavelength or the spectral shift of the photon emitted in the transition.
Cool story, bro.
Quantitative predictions. It was of great comfort to have the logical requirement that the newly created matter begin initially highly redshifted. This idea fitted a whole range of important data very well. Moreover, if the conventional Big Bang theory created matter once, there was no reason why matter should not be created again in later epochs. How dare you? In fact, it would not be strictly a new creation, but merely materialization from mass to energy. Oh, no way. So he would be incorporating that fiction that Neil deGrasse Tyson said in that interview or wrote in his book and was like, mass and energy are equivalent, but you'll never experience it in your lifetime. It happened a long time ago in the universe, and it'll happen again, but just not for us. When we're all dead and gone, like that, then it'll happen again. Like, sick, Neil. That's tight, bro. So yeah, he's throwing a little of that in there, throwing it out there. So from a different, perhaps diffuse location. However, the credo of science, which is instilled in schools, says real scientific theories predict numerical results which can be measured in the more decimal points, the better. I think that's exactly what they can you redshift that to it?
That definitely needs a highlight. Yeah.
That's a redshift, dog.
You need to all uppercap that shit right there. Uppercase all that shit right there. Capital R, capital E, capital A, capital L.
But how many decimal places did we get at this time, boys? All right. Yeah. I was rather gloomy. I was rather gloomy that the age redshift relation would ever be formulated in enough detail in my lifetime to predict the numerical relations. Whatever. Okay. Then something happened which at first I was not aware. In 1977, Janet Narlikar generalized the sacred equations of general relativity. Shout out to your girl, Janet. In the Annals of Physics, we'll have to check that out.
That is my good friend from India, Giant Narlikar.
Can you copy paste that for me? I'm gonna I want to take a look at those generalizing the sacred equations. I want to see what all that entails later. The consequences, I believe, are profound, and I will discuss them at length in the cosmology chapter. But the essence of the solution was very simple. 1. Mass equals a times t squared, where a equals a constant. This means that the particle masses m vary as their ages squared. Since the redshift varies inversely as the mass, we have a numerical relation age of the particle and its redshift, given by equation 2. Where z naught is the redshift of the matter created by t naught years ago, and z sub 1 is the redshift of matter created t sub 1 years ago. We take t naught to be the age of the oldest created matter considered, and for its reference, its redshift to be z naught equals 0. The first part of table 4-3 lists the excess redshift calculated for the matter, which is 1 to 9 million years younger than the matter. Very cool. Shout out to NGC 7702. Comprising the parent galaxy. It is apparent for that matter 3 million years younger than average material in the galaxy. The intrinsic redshift is about 35 kilometers a second. 3 million years is very close to what would be the estimate of how much younger the matter would be in its most luminous supergiants. How do we make this estimate? Looking at figure 4-8, we see essentially the luminosity temperature diagram from the SMC with the brightest supergiants plotted as open circles. The dashed lines indicated tracks along which they evolve rapidly. The stars traverse the uppermost track in just about 3 million years. Now, the stars made of matter of the average age of the galaxy will fill the diagram with the tracks from the stars from a given luminosity faintward. Stars made from matter 3 million years younger will fill in the same tracks plus a brighter track 3 million years younger than the brightest old matter tracks. Since there is an upper limit to the luminosity due to the radiation pressure and the speed of evolution, we will look at the most luminous stars in the galaxy and we will see the stars are made of the youngest matter. The age difference will be about 3 million years. That predicts an intrinsic redshift of about 35 kilometers a second, which is just about the K effect we measure for the most luminous stars in the range of the galaxies previously discussed.
Wow, interesting. I can take back over if you want at any point.
Yeah, I'm going to go grab some water and then tag me back in when you're done.
Cool. So the ages of companion galaxies. What about the ages of companion galaxies? We have discussed in previous chapters how galaxies, particularly in their young and active stages, eject objects and material which later evolve into companion galaxies. Later, we will argue that it is actually the creation of new matter that causes the ejection. But regardless of the process of ejection, whether the ejecta proceed unimpeded along the poles and then fall back to a near orbit, or traverse the plane and emerge slowly, the material is at least somewhat younger than the parent galaxy. However, or how much younger can only be judged by looking at the stars in the companion. Figure 4.9 shows how the color magnitude diagram of the most of the stars in a galaxy would look if we could plot their individual luminosities in colors. The oldest stars have evolved to low luminosities and red colors. As we go to brighter absolute magnitudes, the stars become generally bluer until we encounter the brightest supergiants, which, as we saw in figure 4.8, have very short lifetimes of only a few million years. But when we look at a galaxy that is too far away to resolve very faint stars, we have to deal with a composite spectrum that is an integration of all the stars into one spectrum. Wow, wait a minute. Hold on a minute.
There's a lot of wool pulling going on here, boys.
Yeah. Why do we just get to this? Hold on. That's a big wool pull for real. How much are you deducing from that composite spectrum that's
I
an
was still trying to get over the previous sentence. It's only a few million years. How the hell would you know, buddy?
Yeah, he likes to throw those timelines around. If the composite spectrum is dominated by early type stellar spectra, then we know the majority of the stars are young, and the galaxy itself is probably fairly young. Wow. Hold on. Dude, come on now.
If then probably fairly, you heard the man.
Yikes, wow. This almost
Way to
makes me
quantify that shit. Like,
Yeah,
what
I'm
do we,
almost
yeah,
embarrassed to be reading
home
this stuff
run,
for the
home
moment
run.
here. Barring a necessarily rare major burst of star formation in an old galaxy. If the composite spectrum is dominated by low luminosity stars, we know the galaxy is old, duh, but it is difficult to say exactly how old. For example, if the last track, the 10 billion year old evolutionary track in figure 4.9 was missing, the composite spectrum would look roughly the same, and yet the galaxy would be much younger. If we look closely at the companion galaxies in our local group, the reddest, most dynamically relaxed dwarfs like M32 or NGC 205, see figure 3.1, show some indication of more ultraviolet light, which indicates they are somewhat younger than an old giant E galaxy, but not much. If we say that they are between 10 and 100 million years younger than the parent M31, then they would be predicted by table 4.1 to have between 100 and 1000 kilometer per second intrinsic redshift. This is about what is observed as figures is but that this is about what is observed as figures 313 and 316 in the previous chapter demonstrate. Of course, those with more indicators of young stars like NGC 404, IC 342, and MM82 show higher excess redshifts than the older composite spectra. If we go to companions around higher redshift galaxies, like the companions around NGC 7603 and NGC 1232, we see from the bottom part of table 4.3 that they would have to be about 0.7 and 2 billion years younger, respectively, than their parent
Oh,
galaxy.
obviously,
No
obviously,
problem.
0.7 and 2 billion. Not a week less.
Yeah, stars sometimes, when it comes to stars, sometimes you birth your parent, sometimes your parent births you. It's just.
No, this is 9 decimal places. This is like not even 2 months off. These are the figures.
That is only about 4% younger than the assumed age of 15 billion years for its parent, which would be quite old enough to account for its spectrum. Huh. Even in the NGC 1232 Blue Companion, the companion is identified by a white arrow on the back cover of Quasars, Redshifts, and Controversies and discussed therein on page 88. The required creation epoch is about 2 billion years later, 12%, than the creation of the parent spiral. In the NGC 1232 Blue Companion, however, the spectrum is abnormally, peculiarly blue. Certain old star indicators like NAI and MGI, or I guess that would be sodium iron, or what is the I is
Iodine? Good
iodine? Is that
question.
what that is? Seems right, I guess. Not sure though. Sodium iodine and magnesium iodine absorption are missing, perhaps indicating that the era of the oldest star formation has been pushed to noticeably more recent times than in normal galaxies. Both of the latter two objects are important objects to investigate with the high-resolution imaging and spectroscopy, which is available from the world's giant new telescopes. They are both intrinsically fascinating, and their study would furnish the opportunity to quantitatively explore the same timescales and physical processes of the creation of the most fundamental elements in our universe. In total, there
Confirmation
are.
that is iodine. Sorry.
Thank you. In total, there are already 38 known cases of high excess redshift companions, as mentioned in Chapter 3. They range from plus 4,000 to plus 36,000 kilometers per second, higher redshift than their parent galaxy. Anyone who looks at the examples in quasars, redshifts, and controversies, or the original papers, that being ARP's other book, Astrophysical Journal, those two volumes. Anyone who just looks carefully at the interactions and connections between these high and low redshift galaxies knows they are physically associated. Huh. Most of the companions have spectra indicating unusually large components of young stars and should have been investigated in the greatest possible detail long ago. Yeah. Sounds about right. Does the theory explain the observations? In essence, a theory merely connects together all the known facts in the simplest possible way. We have been driven by the observations to consider what would cause the redshift of galaxy material to decrease as it aged. The only possibilities seem to be that the masses of elementary particles increase with time. We have seen that this satisfies the fundamental constraints of physics as we presently understand the subject, i.e., it is a valid solution of the generalized Einstein field equations. The observations which need to be explained are diverse, ranging from the low redshift K effect excess of young stars to the huge intrinsic redshifts of the quasars. The age of the matter making up the stars which show the K effect can be inferred from stellar evolution theory. The age redshift formula then allows computation of their intrinsic redshift. It is impressive when the predicted redshift is observed to be in agreement with the observed redshift to better than an order of magnitude. Huh. Yeah. Aggregates of stars in the form of companion galaxies can have their ages estimated by the nature of their composite spectra. Ugh. Ugh. It turns out that these estimates. Let's make that pink. It turns out that these estimates predict for their observed intrinsic redshifts to within an order of magnitude. In later chapters, we will show that very large redshifts of quasars are also predicted by the young ages inferred for them. In summary, it is gratifying to note that we have used most of what is known about stars, their composition and structure, spectra, clustering, evolution, in relation to in relation to galaxy morphology. Ugh. You're losing me, Arp. To compute what is causing their non-velocity spectral shifts. This body of knowledge, taken as a whole, has pointed us toward a fundamental property of mass. I mean, I'll stay on this. At least, he's trying to be consistent in his observations, and he's trying to hold them to the same standard. So I do at least respect that. It's just a bummer that he's still kind of caught in that framework. Anyways, I don't need to editorialize. Sorry. The body of knowledge taken as a whole has pointed us toward a fundamental property of mass. It's difficult to imagine how such a wide range of observed phenomena could be explained so satisfactorily if this principle were incorrect. In the coming chapters, it will be exciting to see what insights this gives us into the nature of creation and evolution in the universe. Wow. Okay. So, yeah, there we go. That was chapter 4 of Seeing Red by Halton Arp. We can take a quick little sneak peek next week or whenever we get back into this, chapter 5, the local supercluster. We'll jump into that. This was an interesting closing paragraph, so it's kind of makes me wonder what we'll get into in the coming chapters here. But yeah, thanks everyone for being here, reading along, listening. If you want to join us ever for reading, come join our Discord server. You can go to Discord. Currently, you can go to discord.gg/ether cosmology, and you'll find us there. Or you can just go to ethercosmology.com, click the Discord icon, and that will always link you to our Discord server. And you can follow us in what we're doing over there and join in on the conversations, ask questions, whatever. You can also do that on ethercosmology.com, although I'll be honest, the Discord server is a much busier place. And we do have a Telegram channel as well, so hop over there if you're not already. Especially because you never know, Discord may just shut us down randomly one day. That has happened in the past, so you never know what might happen. So get on Telegram. That way, if the Discord goes down, we can stay in touch. So yeah, thanks everyone for listening in. Tomorrow night we're going to be doing Ether Roundtable on climate change. I have not yet had quite as much time as I would have liked to prepare for that, but in the spirit of the round table, I think we will be all right, and we'll have plenty to talk about and go over. So check that out tomorrow night at 8 p.m. Eastern. And then on Thursday night, we should be doing a live X Twitter space at 9 p.m. Eastern. So check that out as well. And anyone else have any final thoughts or questions before? I guess I kind of just close this out, but anyone have anything that they want to throw in before we wrap this up?
Yep, the science is clear, boys. We'll see you tomorrow.
Boys, I've returned.
Trust the science.
Oh. I ran out of
all about the science.
I ran out of brushtail.coffee.
Oh no. Well,
yeah, it was a real situation. Sorry, that's why I was gone so long. I was savoring my last cup.
Yeah, it was important to savor your last cup, and you should not savor a cup of DS coffee. You should savor a cup of brushtail coffee instead, because it's roasted by me on a grill in a small batch every single time, and is shipped when it's when it's roasted. So you're not going to be getting something out of a bin that was shipped, roasted a week or a month ago. It will be roasted for you for your order, roasted to order, shipped to order. So if you want coffee like that, go to brushtail.coffee, named after my favorite 3 species of penguins, the brushtail penguins. And go check that out if you like high quality coffee.
Those crafty Antarctic seabirds are the best. You're right.
Yeah, those. That's right.
I was in Walmart the other day in the coffee aisle, and I saw all these expiration dates, and I just started laughing because I knew that can only mean one thing. It's automatically DS.
Yeah. Yep. Yeah, it's a fair, different level of coffee. I'll put it that way.
I heard there's a legal limit for the amount of DS that can actually be in there.
No, they can actually put as much DS as they want in there, so long as there's an expiration date.
Oh, okay. All right.
Well, if you're buying, let's say you're buying Folgers or something, or actually whoever, you're buying whatever commodity coffee they call it, then you can have up to 30% Robusta beans in your bean blend. So only 70% will be Arabica. Robusta on its own tastes like rubber. It does have slightly more caffeine, but it's gnarly tasting. And so, 1 year they changed the global commodity coffee market to allow for like 40% Robusta because of like a shortage of Arabica beans or something like that. And globally, as the story goes, quote unquote, globally, around the world, they, or within the world, they changed. The consumption of coffee went down, which I think is interesting. Either people didn't like the taste of their Folgers as much, so they just drank less, or maybe because there was more caffeine. Yeah, the DS was just getting to people.
They could taste
even the
it.
people that thought they didn't care if their coffee was DS. Less, so
they were like, "I'll just go to Dunkin' or whatever they say."
Yup. But I drink the coffee that I like. So if you want good coffee, I curate it for myself. I do it because I love the coffee. So there you go.
Awesome.
Brushtail.coffee. So thanks everyone for listening in. And check us out for coffee night every Monday through Sunday from
Coffee day every day.
noon to midnight over on the Ether Cosmology Discord.